All right, so today we have a nice, tough lecture for you guys. Definitely to make sure you're on the honors track here to be able to put some of this math together. What I want to do first is I would like to talk about your bell work. But for future planning today that we learned today, you're going to have a quiz on Tuesday. I'll also give you your review sheet on Tuesday. We'll do some practice singers on Wednesday, and then you'll have a 2-day test next Thursday and Friday to wrap up this unit. So here's our scenario. It's a hot, hot, hot summer day. You get in your car, and you can sit in the seat, probably feels warm, but what don't you want to touch? That metal buckle, right where it usually gets you in the back of the arm, right? You're like, whoa, okay. Now, I have a few kind of questions to get here. Is the metal buckle any hotter than the rest of the car?
No, it is not hotter than the rest of the car.
Yes.
It burns you because the heat is being transferred from the metal buckle to your own hand. This is called conduction.
Absolutely. Fantastic. So, it's not any different in temperature, right? They're both in the hot car. Let's, for, I don't know, sakes of just using Fahrenheit because we can remember, what's like a hot day? Like if you're in Arizona, maybe like 115 degrees. We're going to use Fahrenheit just because we understand that. Okay? So everything in that room is really, really hot. We agree with that, right? And your body temperature in Fahrenheit is what? 98 degrees. So we agree that everything is hotter than you. Okay? So when you sit in there, energy is being transferred to you. Now, like, conduction is how you touch it, and it's everything is having energy go to you, but why isn't the seat burning you? Why is it just the metal buckle that is burning you? What terms do you think we're looking for here? Go for me. Perfect. You got it. The seat is an insulator and the metal buckle is a conductor. So while they're both trying to give you energy just as quickly as they possibly can, the conductor can transfer energy to you faster than the seat. The seat's trying with all its might, like, I want to give you my energy. And it's trying, but it can't because it is an insulator. But that buckle, boy, that will give you some joules very, very quick. Okay? Does that make sense? So I don't want you to forget some of the easy stuff in this unit. That shouldn't hopefully be like hurting your brain too much. Because on the test you'll have some thinkers that might have to do with insulators and conductors, and then you'll have some questions that might have to do with the math we're about to do. But so everybody understands, so seat is an insulator, buckle is a conductor, then therefore it will burn you a whole lot faster. All right, so let's do this. Thermochem notes number 5. And you can tuck that bell work away. You don't need it, unlike the other days where I'm like, you still need that. That was just to get your brain warmed up. Let's do it. All right, so I highly, highly, highly suggest that you keep out this chart from yesterday because we're going to reference this a lot. I used to not use this when I was teaching. I used to think that you could kind of visualize the different steps, but I have found that some students rely heavily on this graph to tell them what steps to take. So if you can visualize this graph and you don't necessarily need it, that's fine. But if you need kind of like a road map of where we're going and you want to use this graph, you can. You clearly won't have it on the test, but you can always draw it in the corner or do whatever you need to do, okay? So let's just refresh what this is. Yesterday we talked about how you can warm a solid, and we're talking water today, water only today. You could do these calculations with any substance, but water is what we're most comfortable with. Water is a lot of what, is going on in our world, so we use water for this idea. So our water can be a solid up to 0, but once water gets to the temperature of 0, the solid has to stop and melt. And I think one of the big ideas we need to understand is that over here it is a solid at 0, and over here it is a liquid at 0 degrees Celsius. Does that make sense? It just went through a phase change and all it did was melt, but it kept its temperature at 0. Then you can have liquid water anywhere between 0 and 100. Once you get to 100, though, the temperature stops. And remember yesterday in our lecture we said you could keep adding energy, but now all that energy is going in to change the state instead of the temperature. So over here we're liquid water at 100, and then over here we're gas water or vapor at 100. Okay, and then your gas can warm up again. So if you can understand this in your head and you can keep this nice and organized, okay, today is multi-step math. So let's go through. So we have 4.18, you don't break this part. We got 4.18 joules per gram degree Celsius. And we have always been using that number, but that's really, really nice because that is the units that, or the specific heat capacity you have for liquid water. So that's just in that range there. Ice and steam just have a different amount of energy that need to heat it and cool it. So 4.18 doesn't work for solid and 4.18 doesn't work for gas. So let's just have a look-see here and put a little chart in your notes if you would like. And if you want to write water phase, you can or whatever. Or you can just write solid, liquid, gas. And we're going to get you the specific heat capacities for those states of matter. Solid, liquid, gas. And we're going to get you the specific heat capacities for those states. God bless. Okay. So we all know the liquid. You can always already fill this in. Liquid, for liquid water, the specific heat capacity is 4.18 joules per gram degree Celsius. We got that one. A solid ice cube doesn't take as much energy. You would probably notice if I put an ice cube right now, it would immediately start melting. It would take energy from the environment around it into it to melt it, to speed up its particles. The specific heat capacity, or the C value, so if you're not remembering what we're talking about in Q is equal to MC delta T, the C value for a solid water or an ice cube is 2.06 joules per gram degree Celsius. So just around a half of the amount of energy it takes to heat and cool water, liquid. And gas takes a touch less than that. The specific heat capacity for a gas is 2.02 joules per gram degree Celsius. Okay, so what I'm saying is that on here, in order to heat and cool solid, we need 2.06 joules per gram degree, and to heat and cool a gas, we need 2.02 joules per gram degree. Does that make sense? Just because they're a different nature, they kind of have different structure, all that kind of good stuff. Now let's take into another question here. So that's what I kind of just use this idea here. Everybody got those numbers? Now, our heat equation, Q is equal to MC delta T, works fine to warm a solid, works fine to warm a liquid, works fine to warm a gas. Thinking, why can I not use Q is equal to MC delta T to figure out how much energy it would take to melt or freeze or condense or vaporize? What don't we have in those things? Talk to me. You don't have a delta T. So can I use Q is equal to MC delta T when I'm talking about a phase change? You can't. There's no delta T. You can't throw a zero in there. It would wreck everything. So we have to think of a different idea. So that's fantastic. There's no phase change, or there's no delta T when you have a phase change. So let's do this. So you don't have to write any of this. Let's just go. So during a phase change, we're going to do a different thing, and you don't have to write this because we'll write two different ones. But during a state or phase change, we are only going to take our mass times a given amount of energy we know it takes to melt, or a given amount of energy we know it takes to freeze. Okay? So let's talk about those two. Are you ready? Here's the first one. Let's write this down. It says heat of fusion. Heat of fusion. The word fusion used to mean a lot to me that meant melting. Fuses are things that you might, if you have a breaker box that isn't the clicker kind and just has a fuse in it. What a fuse used to do is if electrical energy tried to run through a fuse, it would melt to stop a big surge of energy coming in. Now you probably have a breaker box where you just have to flip the thing if you turn on your hairdryer, your microwave, and your water heater all at once or whatever. So fusion to you should mean melting, okay, or freezing. Heat of fusion is directly associated to melting and freezing. So if I am going to, and I kind of think of this idea here, think of it as like a road trip, and you have to pay some tolls. How much money would I have to pay to melt my ice cube? How much money would I have to pay to boil my liquid water? So we're going to see how much, and it depends on how much mass you have. So that number, okay, is the energy needed to melt or freeze 1 gram of a solid if it's at its melting point. Energy needed to melt or freeze 1 gram, and we're talking about water all the time. Water, water, water. At its melting point. So once you warm it up to 0, how much does it cost? And that number for water, big idea, you want to write your notes here. Delta H of fusion for water, it takes 334 joules to melt every gram of water. 334 joules to melt every gram of water. Okay, so we're talking, when you get to this step here, so you can do a Q is equal to MC delta T to figure out how much energy it takes to get my solid ice cube to get up to 0. But then when I want to see how much energy it takes to melt that solid, I would take my mass times 334 joules. Okay, awesome. Obviously, it's going to take a different amount of energy to vaporize and condense, so this is called the heat of vaporization. Oh, geez, you are, I'm sorry. Got it. Heat of vaporization will be the next one. And 34 joules per gram.
There.
Perfect. Thank you. All right, so heat of vaporization is now going to be the amount of energy that we need to vaporize or condense our water. And this all happens around 100. So if you can think about vaporizing or condensing, or if you would like to write the big, I don't care which one you write here, the heat energy needed to vaporize or condense 1 gram of a liquid at its boiling point. Maybe you just write heat of vaporization is all about vaporizing and condensing. Now we're going to think about it. We are trying to take, and we're thinking on our entropy scale, we're trying to take liquid water and make it a gas. That is a huge entropy jump. So this number is going to be huge. Okay, in order to take liquid water that's stuck to it, another liquid water, and make it a gas where it can move independently, jump in our entropy, this number is gigantic. 2,260 joules for every gram to be vaporized. It's a big, big, big cost. 2,260 joules to make every gram of water turn into a gram of gas. But we know it takes a whole lot on the entropy scale to become from a liquid to an independently moving gas. Okay? So that's how many joules per gram. So what I would like to do now, and I don't usually like to do practice problems in your notes, but I'm going to change that on its ear, so when you do get to the semester exam, all that kind of good stuff, you have an example in your notes instead of just on the worksheet. And I'm going to show you as hard as the examples can get, and then you guys will do shorter ones on your practice paper. Okay? So what I want you to do, I'd like for you to, we can paraphrase this, but I'd like for you to jot this in your notes. So say how much energy, and I would write this down so you got this, and you need a decent amount of paper. I would say you need like at least like 7 lines left. Okay? How much energy is required?
Excuse me, can you go back to the last one?
Did you get that 2260? Got it.
I just need to write. There.
You got it. Okay. Now we're writing this question down, and then you need some space. Yeah, that looks like a good choice. Nice. How much energy is required to warm a 265 gram ice cube? And the ice cube is going to be at negative 15.4 degrees. And I'm going to take it, I call it from like New York to LA. We're going to take it the whole way, as far as it can go. We're going to take it from a very cold solid, and I'm going to take it to a very warm, right near the temperature we got our steam yesterday, 185 degrees Celsius. Okay. Now I'm going to show you how to do some steps where you write out the actual process, because sometimes I think that helps. If you eventually can jump into just doing the math, you don't have to write the words down. But I think it's a good idea to write the words down to get us started. Okay, so this is going to kind of make a little bit of sense here. So I got some information here for you guys. Okay, and we will deal with this here in a second. But what I want to do is I'm going to write some words. Whoa, don't get angry. I'm sorry. It doesn't like this lecture either. Now, the first thing I want to do, if I'm thinking about on my kind of my heating and cooling curve here, I'm way down here at negative 15.4 degrees Celsius. Do we all agree with that? Can I melt my ice cube at negative 15.4 degrees Celsius?
No.
Ice cubes melt at 0, right? So the first thing I need to do, and again, we're going to start with some words, and then eventually if you don't want to write the words, you don't have to, but let's write it out for our first practice problem. The first thing you need to do is you need to warm your solid to 0. Does everybody agree with that? We have to warm our solid up to 0 so that we can then melt it. So that's going to be how much energy it takes to get us to this point on our graph. Can we continue warming our ice cube above 0? We stop and we have to do a phase change. What phase change is that called? Then we have to pay to melt it. So then we have to pay to melt the ice cube. It's a very tiny eraser. Once we have paid to melt the ice cube, we are now traveled to that checkpoint. I think of them as like tolls. How much did it take to go on that road? Now, I am liquid water, but I'm at 0. Can I boil at 0? I boil at 100. So then we have to figure out how to warm the liquid to 100 degrees Celsius. Yes? Perfect. Then that means I've traveled this portion. Boom. Now I'm liquid at 100. Can liquid water get any hotter than 100? No. So we have to stop and pay to vaporize it or boil it, whatever you want to say. Boil the liquid. Then that pays for this section of the toll. Now I am a gas, but I'm at 100 degrees Celsius. Does it want me to be a gas at 100? It wants me to be a gas at 185. Okay? So the last step is I got to heat my gas to 185. Now, on your practice problems, you might not always have to go the whole way. I might start you and I'll say, hey, here's your liquid water. I want you to make it an ice cube at negative 20. Or I might say, here's your 0 degrees ice cube. I just want you to melt it. Okay, so there's a whole bunch of different pieces and parts, but we'll practice this. Okay, I consider this the hardest thing in this unit. Now, let's quantify this. We have, and you will always, let me tell you this right now before I forget, I will always give you this information. Do not think that you have to memorize this, okay? But with that said, over here, you can use Q is equal to MC delta T. This is when we are in a state and we are warming and freezing. I'm sorry, we are warming and cooling. Over here, you just take your mass times your given to figure out your state change. Okay, so let's see. We're going to do a couple Q's here. Let's go like this. If I am warming my solid to 0, do I have a delta T? Yes? So the first thing I'm going to do is I'm going to do Q is equal to MC delta T, and I like to write them 1, 2, 3, 4, 5. It's up to you. So for Q1, looking at my question, what is the mass going to be of my ice cube? Q is equal to M, which is 265. I heard somebody whisper it. Good job. 265 times my C, be very careful for my solid, is 2.06, right? And careful, how many degrees am I going to go if I can't take a straight shot up to 185. I have to go from negative 15 to 0. So that's going to be a difference of 15.4. Perfect. Okay. Now, that is just how much energy I had to spend to get my ice cube up to 0. Then the next thing I need to do is I need to pay to melt it. Can I use a delta T, Q is equal to MC delta T, to melt it? No, you cannot. So you're going to take your mass, which was 265, and you're going to multiply it by the delta H for what we're trying to do. And remember, we said fusion means melting and freezing. That's going to pay us to get the next bit. So now we're here. Q is equal to MC delta T. I can do this again. This will look very familiar. I have my M, my 265. I'm going to multiply it. Now it's a liquid because I just melted it, so times 4.18. And I want to go 100 more degrees, from 0 to 100. Now I'm up here. I need to stop and I need to pay to boil it. Do we have a delta T when we're boiling? Nope. So we're going to do M times delta H, but the delta H we're going to use now is our vaporization. So I'm going to do 265 times 2260. Now I have crossed the bridge of vaporization, and I just want to get my gas. Here's the last tricky part. I'm going to warm my gas, so I'm back to Q is equal to MC delta T. Q is equal to M. Then I look up my C for gas, which is 2.02. Carefully, what is my last delta T? How'd you get 85? Did we already pay to get to 100? And now I got to pay it to go 85 more degrees, and that's it. Okay? Are you with me? It's tough stuff. Okay? Now, what you're going to do, and I know, but you guys can all punch these numbers in your calculator, so let's just jot some of these down. If I do 265 times 2.06 times 15.4, you get 8,406 joules. 0.9. If I do 265 times 334, you get 88,510 joules. If I multiply 265 times 4.18 times 100, clearly that's going to be a lot. I get 110,770 joules. Another big number, if I take my mass and times it by how much it takes to vaporize it, I'm going to get 598,900 joules. And you don't have to write joules on every single one on your work, no worries. And then to get that steam to warm up the last 85 degrees, I'm going to go 45,500.5 joules. Now, if you had to go on a road trip and you paid $10 for that ride and $20 for that ride and $15 for that ride, what would you do to figure out the total cost? You would add them up. Boom. Shakalaka. Okay? Mic drop. So, this seems very simple when I'm doing it for you. And on purpose, what I have done is I have cut out a lot of time in this lecture to make sure that you will have plenty of time to practice. Because not every single question is going to go from New York City to LA. Some of these people consider easier, and some people consider them harder. You got it. You got it. You got it. All right, so let's figure out. So this is the whole way. The biggest thing is trying to figure out how many steps you need. Okay? So, if you would write very large on here, quiz on Tuesday. I'll give you a bell work tomorrow right before our lab. You probably won't do it, that's okay. Because our lab is going to be super fun. We'll talk about our lab here in a second for tomorrow. And then we'll practice it again on Monday. We'll take our quiz on Tuesday. I suggest underneath each of these writing the formula that you need. So if you are warming or cooling a phase, you may use Q is equal to MC delta T. So I would jot that down under this one. If you are doing a phase change, you have to do Q is equal to M delta H. And delta H just stands for 334 if you're freezing or melting, and 2260 if you are vaporizing or condensing. So I put some of the harder ones up here first, and I'll do a couple of the hard ones with you, and then we'll go. Calculate the number of joules needed to turn a 525 grams of water at 100 degrees to steam at 100 degrees. The biggest thing we have to think of is how many Qs do we need? On this kind of graph here, if I am water at 100 degrees, I'm right up there. We agree? And if I'm steam at 100 degrees, I'm right over there. How many steps do you think we have to drive? 1. Okay? So all I have to do is vaporize that liquid. If I'm in a phase change, do I have a delta T? No. So all I'm going to do is one of these bad boys. A Q is equal to M delta H. My mass, we said, is 525. Oh, dear. Wrong Q. Whoa. No more than that. Come back, paper. Not oriented. Okay, so we're vaporizing. So I have my M, which is 525. What am I going to multiply that against of these two if I am trying to vaporize it? 2260. And when you multiply those two things together, 525 times 2260, I get a large number. 1,186,500, and the unit for Q is always going to be joules. Okay. I'm going to set you up on the next one here, and then I want to see if you can't do the rest by yourself. Because I know some of you are like, got this, and some of you are like, what? So I think I should come around and see how we're doing. Number 2, calculate the heat energy, the thermal energy needed to change 15 grams of ice at -50 to water at 50 degrees. So let's think this through. I'm way down here. I'm at -50. That's my solid. I want to be liquid water at 50. How many Qs am I going to need? Well, the first thing, if I'm at -50, can I melt at -50? So the first thing I need to do is I need to warm up to 0, right? So you got to warm your solid to 0. Then I have to stop and pay the cost to do what phase change? I got to stop to melt. So that would be this next step right here. Now I'm a liquid at 0. Do I want to be a liquid at 0? I want to be a liquid at 50. So then I'm going to warm my liquid to 50 degrees. So all I want you to do, when it says warm or cool, you're going to use Q is equal to MC delta T. When it is a phase change, you just do M delta H. Okay, so I see a lot of people going. I'm going to stop right here, see if you can't fill in those steps, and then you're going to have to start reading them and doing them by yourself. So I'm going to bring around a key. Hopefully we're feeling good. Again, very tough stuff, but I think you guys are doing great.